So we've seen the definition of the derivative here. The limit as x goes to a of f of x minus f of a over x minus a. That's equal to the derivative of f at the point x equals to a. We've seen that what this is a limit of difference quotients, each difference quotient representing the slope of the secant line between the points a, f of a, and the points x, f of x. And that limit becomes the slope of the tangent line. So what I want to do right now is show you another equivalent definition of the derivative that we like to use. We use this all the time. Sometimes it makes the computations easier. Sometimes we like to use it for proofs. Just depending on the situation, it can be a little bit more convenient. So what I'm going to do here is a change of variable in the limit. And I'll explain what I mean in a second, but first let me kind of draw you a picture that shows what's going on here. So maybe you've got some function f, and maybe you picked a point x equals to a. And when you're calculating this limit, let's look at, you have to imagine that x is very close to a, but I draw it so that you can see it. And you can go up here and look at the point x, f of x, and you draw the secant line in between them. Okay, and you imagine x getting closer and the secant line's getting closer and closer to the tangent line. So that's all fine. And what I'm going to do here is I'm going to make a change of variable. So instead of considering that x is getting close to a, I'm going to consider that the distance between a and x is getting close to 0. So this distance is going to be getting close to 0 as x is getting close to a. So that's the motivation. And so here's what I'm going to do. So I'm going to write a new variable, h. Often we use h for the step size or for the distance, or more properly, the signed distance. It's going to be positive if x is bigger than a, and h will be negative if x is less than a. We call that the signed distance. So its absolute value is equal to the distance. So I'm going to write h equals to x minus a. And I'm just going to rewrite this limit using that. So here on the picture, h represents that distance from a to x, unless x is below a, and then it'll be the negative of the distance. But either way, it's going to be equal to x minus a. So now I just want to rewrite this limit. And as x goes to a, surely x minus a goes to 0. So I'm going to be taking a limit as h goes to 0. And now I want to replace x with what it's equal to. So x is equal to a plus h. So I get f of a plus h. And then I just subtract f of a. And then I divide by x minus a, which is equal to h. And so there you have it. So this is another way of thinking about the derivative. It's also completely equal to f prime of a. So you can either think of this definition, which has geometric significance, that is to say, the geometry is the secant line, so you're looking at the limit of their slopes. You can also think of it as, this way is the distance going to 0, and you just get f of a plus h minus f of a divided by h.